Hello and welcome back. In today's video, I'm overclocking the AMD Ryzen 7 7800X3D processor all the way up to 5.4 GHz using the ASUS ROG Crosshair X670E Hero motherboard and Eclk Quantum Custom Loop water cooling. In an ironic twist of events, I found that the successor to the locked 5800X3D is the most tunable X3D processor yet, and I genuinely enjoyed exploring the various overclocking strategies to squeeze more performance out of this 7800X3D processor. I hope you equally enjoy the video that I've prepared for you. Alright, we have a lot to cover too, so let's get started. The AMD Ryzen 7 7800X3D is the direct successor of AMD's very first X3D CPU, the Ryzen 7 5800X3D. It is also part of the third wave of AMD Ryzen 7000 AM5 processors. The first wave of Zen 4 Ryzen 7000 processors launched on August 29, 2022 and consisted of 4 SKUs ranging from the 6-core Ryzen 5 7600X to the 16-core Ryzen 9 7950X. The second wave of Ryzen 7000 processors launched on January 4, 2023. It consisted of 3 non-X SKUs ranging from the 6-core Ryzen 5 7600 to the 12-core Ryzen 9 7900. The third wave of Ryzen 7000 processors, also announced on January 4, but only available since February 28, consists of exclusively X3D variants with the 3D V-Cache. The lineup consists of 3 SKUs, ranging from the 8-core Ryzen 7 7800X3D to the 16-core Ryzen 9 7950X3D. We already overclocked the Ryzen 9 7950X3D in SkatterBencher number 56, the Ryzen 9 7900X3D in SkatterBencher number 58, and the 5800X3D in SkatterBencher number 39. I won't say too much about the technical aspect of 3D V-Cache, as plenty of other media will cover that part of the X3D story. Long story short, AMD has 3D stacked additional L3 cache on top of the CCD to expand the on-die cache capacity. That, in theory, should help improve the performance in latency-sensitive workloads. The Ryzen 7 7800X3D has one 8-core CCD and 16 threads. The base frequency is 4.2 GHz and the maximum listed boost frequency is 5 GHz. The TDP is 120 watt and the PPT is 162 watt. In this video, we will cover 5 overclocking strategies. First, we rely on AMD PBO and EXPO performance boost technologies. Second, we use the ASUS X3D OC profile available in the BIOS. Third, we tune Precision Boost Overdrive with Curve Optimizer. Fourth, we rely on asynchronous Eclk mode. Lastly, we pursue a manual overclock. However, before we jump into the overclocking, let's first have a look at the hardware and the benchmarks that we'll be using in this guide. The system we're overclocking today consists of the following hardware. The Elmolabs Easy Fan Controller is the base version of the EFC SP that I already covered on my channel. I also have already covered how I use the Elmolabs Easy Fan Controller in my overclocking guides. To make a long story very short, I connect the EFC to the EVC2 device to monitor the ambient temperature, water temperature, and fan duty cycle. I also include these results in my Prime 95 stability tests. I also use the Elmolabs EFC to map the radiator fan curve to the water temperature. Without going into too many details, I've attached an external temperature sensor from the water in the loop to the EFC. Then I use the low-high setting to map the fan curve from 25 to 40 degrees water temperature. I use this configuration for all overclocking strategies. The main takeaway from this configuration is that it gives a good indicator of whether the cooling solution is saturated. We use Windows 11 and the following benchmark applications to measure performance and ensure system stability. Before we start overclocking, of course, we have to check the performance at stock settings. Please note that the Precision Boost 2 boosting algorithm governs or manages the performance over base specification. The standard parameters of the Precision Boost algorithm for the Ryzen 7 7800X3D are as follows. We use the Shimano boost curve and SuperPi 32M to check the CPU boost behavior and per core maximum effective clock frequency. The boost frequency when one thread is active is about 4758 MHz and trails off to 4486 MHz when all cores are active. We also find that 4 out of the 8 cores are boosting beyond the maximum advertised boost speed of 5 GHz. That's not surprising, as we know that the programmed if max is 5050 MHz, but it's always nice to see a processor over-deliver on its promise. Here is the benchmark performance at stock. Here are the 3D Mark CPU profile scores at stock. When running Prime 95 small FFTs with AVX512 enabled, the average CPU effective clock is 4285 MHz with 0.937 volts. The average CPU temperature is 65.7 degrees Celsius. The ambient and water temperature is 24.9 and 29.9 degrees Celsius. The average CPU package power is 71.9 watts. When running Prime 95 small FFTs with AVX disabled, the average CPU effective clock is 4531 MHz with 1.011 volts. The average CPU temperature is 75.7 degrees Celsius. The ambient and water temperature is 24.8 and 29.9 degrees Celsius, and the average CPU package power is 75.7 watts. Now let us try our first overclocking strategy, but before that, make sure to locate the Clear CMOS button. Pressing the Clear CMOS button will reset all your BIOS settings to default, which is helpful if you want to start your BIOS configuration from scratch. However, it does not delete any of the BIOS profiles previously saved. The Clear CMOS button is at the rear I/O panel. In our first overclocking strategy, we make advantage of AMD exclusive performance tuning technologies, Precision Boost Overdrive 2 and EXPO. With the launch of Zen 3, AMD introduced an improved version of Precision Boost Overdrive. They call this Precision Boost Overdrive 2. This toolkit gives us manual control over some of the parameters that are governing the Precision Boost 2 boosting algorithm. Precision Boost Overdrive 2 builds on the PBO implementation of Zen 2. In addition to the platform overclocking knobs from Zen Plus, PPT, TDC and EDC, and processor overclocking knobs from Zen 2, Boost Override and Scalar, Precision Boost Overdrive 2 introduces Curve Optimizer. There are essentially 3 levels of Precision Boost Overdrive. AMD's stock values, which can be set by disabling PBO, the motherboard vendor values, which are programmed into the BIOS to match the motherboard VRM specification and can be set by enabling PBO, and custom values, which the end user can program. I explore the ins and outs of Precision Boost Overdrive 2 tuning in my AMD Raphael overclocking launch video. In this overclocking strategy, we're simply enabling PBO, whereas in the next strategies, we'll also start tuning with some of the PBO tools. We rely on the motherboard's pre-programmed PBO parameters by enabling Precision Boost Overdrive. We find that the following values have changed. For previous Ryzen CPUs, increasing the platform boost parameters substantially impacted the performance, especially on higher core count CPUs. For Ryzen 7000X series processors, however, AMD's default platform parameters are relatively unconstraining. For the 7800 X3D, it's clear that the platform boost limiters are not the constraining factor. During a Prime 95 non-AVX workload, we see that the maximum values for PPT, TDC, and EDC are 75 watt, 60 amps, and 60 amps respectively. The main limiting factor for the 7800 X3D is the maximum allowed voltage of around 1 volt under a high load. EXPO stands for AMD Extended Profiles for Overclocking. It's an AMD technology that enables ubiquitous memory overclocking profiles for AMD platforms supporting DDR5 memory. EXPO allows memory vendors such as G.Skill to program higher performance settings onto the memory sticks. If your motherboard supports EXPO, you can enable higher performance with a single BIOS setting. So it saves you from a lot of manual configuration. While our memory kit is rated at DDR5 6400, I had to run it at DDR5 6200 because higher frequencies weren't stable with this particular CPU. Upon entering the BIOS, go to the Extreme Tweaker menu. Set AI Overclock Tuner to EXPO 1. Set memory frequency to DDR5 6200. enter the Precision Boost Overdrive submenu. Set Precision Boost Overdrive to enabled, then save and exit the BIOS. We use the Shamino boost curve on SuperPi32M to check the CPU's boost behavior and per-core maximum effective clock frequency. Since enabling PBO doesn't alter any of the CPU's operating frequencies, there's no difference to stock. We reran the benchmarks and checked the performance increase compared to the default operation. As expected, enabling Precision Boost Overdrive does little to improve the system performance. After all, the CPU is primarily limited by the operating voltage, not by any platform power parameters. Thanks to enabling EXPO, we still get a performance improvement of plus 4.71% in Geekbench 6 Multi. When running Prime 95 small FFTs with AVX 512 enabled, the average CPU effective clock is 4289 MHz with 0.936 volts. The average CPU temperature is 67 degrees Celsius. The ambient and water temperature is 25.3 and 30.7 degrees Celsius. And the average CPU package power is 84.8 watts. When running Prime 95 small FFTs with AVX disabled, the average CPU effective clock is 4532 MHz with 1.007 volts. The average CPU temperature is 81.3 degrees Celsius. The ambient and water temperature is 25.1 and 30.4 degrees Celsius. And the average CPU package power is 89.1 watts. In our second strategy, we leverage the ASUS X3D OC profile that's embedded in the BIOS. Why recently ASUS has relied almost exclusively on their AI overclocking technology to provide a means for automatic overclocking, ASUS has a long history of providing customers with easy paths to extra performance. Those easy paths typically consist of having hard-coded BIOS profiles, which the user can enable with a single click of a button. The X3D OC profile is a return to this old-fashioned style of overclocking. The profile uses a synchronous Eclk to overclock the Ryzen 7 7800 X3D processor. We'll get back to how this works later in this video. For now, it suffices to say that the profile sets the Eclk frequency to 104 MHz and thus overclocks our CPU by 4%. Note that the X3D OC profile does not adjust the Precision Boost power limits. So you want to enable Precision Boost Overdrive and ensure the PPT, TDC, and EDC are set accordingly to maximize the performance. Upon entering the BIOS, go to the Extreme Tweaker menu. Enter the Overclocking Presets submenu. Select Load X3D OC Profile. Leave the Overclocking Presets submenu. Set AI Overclock Tuner to EXPO 1. Set memory frequency to DDR5 6200. Enter the Precision Boost Overdrive submenu. Set Precision Boost Overdrive to enabled, then save and exit the BIOS. We use the Shamino boost curve on SuperPi32M to check the CPU's boost behavior and per-core maximum effective clock frequency. The X3D OC profile increases the precision boost frequency by about 4%. Thus, our new Fmax is 5250 MHz. This overclock translates nearly 1-to-1 to both the boost curve and the per-core maximum effective clock frequency. The boost curve now runs from 4852 MHz to 4668 MHz. And we find that 4 out of our 8 cores are now boosting beyond 5.2 GHz in light workloads. We reran the benchmarks and checked the performance increase compared to the default operation. With a 4% CPU overclock, the performance increased by about 4% in all of our benchmarks, including the single-threaded workloads. We now have a maximum performance improvement of plus 8.42% in Geekbench 6 Multi. When running Prime 95 small FFTs with AVX 512 enabled, the average CPU effective clock is 4446 MHz with 0.935 volts. The average CPU temperature is 69.1 degrees Celsius. The ambient and water temperature is 25.7 and 31 degrees Celsius. The average CPU package power is 88.1 watts. When running Prime 95 small FFTs with AVX disabled, the average CPU effective clock is 4700 MHz with 1.004 volts. The average CPU temperature is 83.6 degrees Celsius. The ambient and water temperature is 25.4 and 30.8 degrees Celsius. The average CPU package power is 92.1 watts. In our third overclocking strategy, we will use the Curve Optimizer tool included in the Precision Boost Overdrive 2 Overclockers Toolkit. As I mentioned already, Curve Optimizer is a very important new tool included in the Precision Boost Overdrive 2 toolkit. Curve Optimizer allows us to fine-tune the VFD curve of every core inside our CPU. The VFD curve is a factory-fused curve that defines what voltage is required to run a CPU at a certain frequency and a certain temperature. The higher the frequency or the higher the temperature, the more voltage you need. Curve Optimizer adjusts the VFD curve by offsetting the voltages of the factory-fused VFD curve. By setting a positive offset, you can increase the voltage point. Conversely, you decrease the voltage point by setting a negative offset. You can offset the entire curve by up to 30 steps in a positive direction and up to 300 steps in a negative direction. The traditional approach of a Ryzen overclocking is to use a negative curve optimizer. Two things happen when you do that. First, you tell the CPU that it needs less voltage for a given frequency, and as a consequence, at a given voltage, it can apply a higher frequency. Second, the CPU temperature will be lower because you use less voltage at a given frequency. That extra thermal headroom will also encourage the Precision Boost algorithm to target higher voltages and frequencies. As I mentioned already, Curve Optimizer is available on a per-core basis, and that gives us a tangible benefit because some cores overclock better than other cores. However, for this OC strategy, I will stick with an all-core Curve Optimizer. The manual tuning process for curve optimizing can become quite convoluted because it spans a wide range of scenarios, from single light threaded workloads to heavy all-core workloads. My particular process for curve optimizing this Ryzen 7 7800 X3D was as follows. In my case, I used an all-core curve optimizer of -35. I will show you the BIOS settings in a minute, but first, please note that these values, the curve optimizer values, are very CPU specific, and the optimal values for your CPU may be substantially different than the values that I've used for this CPU. Upon entering the BIOS, go to the Extreme Tweaker menu. Set AI Overclock Tuner to EXPO 1. Set memory frequency to DDR5 6200. Enter the Precision Boost Overdrive submenu. Set Precision Boost Overdrive to Enabled. Enter the Curve Optimizer submenu. Set Curve Optimizer to All Cores. Set All Core Curve Optimizer sign to Negative. Set All Core Curve Optimizer magnitude to 35. Then save and exit the BIOS. We use the Shimano Boost Curve and SuperPi 32M to check the CPU boost behavior and the per core maximum effective clock frequency. While Curve Optimizer doesn't increase the CPU's maximum boost frequency, it does push the CPU to run at higher frequencies. We find that the boost curve has risen by about 200 to 300 MHz compared to stock, and that every single of the 8 cores now boost to 5050 MHz. That's 50 MHz higher than the AMD advertised boost frequency of 5 GHz. Talk about over-delivering on your promise. We reran the benchmarks and checked the performance increase compared to the default operation. Curve optimizing this Ryzen 7 7800 X3D processor surprisingly effectively extracts more CPU performance. While, unlike with the OC profile, we can't increase the maximum boost frequency, in medium to heavy workloads, curve optimizing pushes the CPU frequency higher than the X3D OC profile. Hence, we see a nice performance improvement in most benchmarks. We get the maximum performance improvement of plus 9.19% in Geekbench 6 Multi. When running Prime 95 small FFTs with AVX 512 enabled, the average CPU effective clock is 4538 MHz with 0.915 volts. The average CPU temperature is 67.1 degrees Celsius. The ambient and water temperature is 25.6 and 30.8 degrees Celsius. The average CPU package power is 85 watts. When running Prime 95 small FFTs with AVX disabled, the average CPU effective clock is 4800 MHz with 0.986 volts. The average CPU temperature is 81.5 degrees Celsius. The ambient and water temperature is 25.6 and 30.9 degrees Celsius. The average CPU package power is 89.1 watts. In our fourth overclocking strategy, we will leverage the return of Eclk mode. Eclk stands for external clock and is exactly what the term suggests. We can use an external clock for the reference clock. This was previously available on a Ryzen 2000 Pinnacle-rich CPUs, but was removed afterward, until now. The standard Raphael platform has a 48 MHz crystal input to the integrated CGPLL clock generator. The CGPLL then generates a 48 MHz clock for the USB PLL and a 100 MHz reference clock for the FCH, which contains the CCLK PLL for the CPU cores and several SoC PLLs. The external clocks are inputs to the FCH. There you can configure how you want to use the external clocks. Raphael supports up to 2 external clock modes. They're called Eclk 0 mode and Eclk 1 mode. In Eclk 0 mode, an external 100 MHz reference clock is used for both the CPU and SoC PLLs. In other words, it's a reference clock that affects the CPU core clocks as well as the PCIe and SATA clocks. In Eclk 1 mode, there are 2 distinct external 100 MHz reference clocks. One clock provides the 100 MHz input for the CPU PLL, and another provides the 100 MHz reference clock for the SoC PLLs. In previous SkatterBencher guides, the ones before Ryzen 7000, I refer to the practice of using reference clock overclocking as supercharging PBO. But unlike previous Ryzen processors, reference clock overclocking is very well supported on the Ryzen 7000 CPUs, and it provides us with a viable path for overclocking. The overclocking strategy with Eclk is the polar opposite of what we are used to with Ryzen CPUs. OC strategy number 3 shows that Ryzen overclocking is typically done with a negative curve optimizer. That pushes the precision boost algorithm to reach higher boost frequencies. With Eclk, we still build on the factory-fused VFD curve, but adjust the frequency by adjusting the reference clock. For example, if the precision boost has a VFT point for 4500 MHz at 1 volt at 50 degrees Celsius, with an Eclk of 105 MHz, the actual point will be 4725 MHz at 1 volt at 50 degrees Celsius. The default voltage for this VFT point won't suffice for stable operation. So counterintuitively, we use a positive curve optimizer to increase the voltages of the VFT point. For example, a plus 30 curve optimizer may increase the voltage by 150 mV. Thus, the resulting VFT point will be 4725 MHz at 1.15 volt at 50 degrees Celsius. Note that the voltage increase is still subject to the precision boost limiters. The maximum voltage for a 7000 X3D processor is 1.2 volt, regardless of the curve optimizer setting. Suppose curve optimizer doesn't provide you with sufficient additional voltage. In that case, you can always add a voltage offset via the VRM controller configuration. One more critical point. Eclk also affects the maximum frequency ceiling. With an Eclk of 105 MHz, the newly programmed Fmax for the 7800 X3D is 5.3 GHz. If that's too high for your CPU, you can always reduce the Fmax by setting a negative CPU boost clock override. The manual tuning process for using Eclk reference overclocking can become quite convoluted because it spans a wide range of scenarios from single-threaded light workloads to all-core heavy workloads. The process that I followed for this Ryzen 7 7800 X3D was as follows. In my case, I used an Eclk of 107 MHz and a curve optimizer setting ranging from -5 on core 6 and +10 on core 3. I'll show you the BIOS configuration in a minute, but first, please note that these settings are very CPU specific, and the optimal values for your CPU may differ substantially. Upon entering the BIOS, go to the Extreme Tweaker menu. Set AI Overclock Tuner to EXPO 1. Set Eclk mode to asynchronous mode. Set BCLK2 frequency to 107. Set memory frequency to DDR5 6200. Enter the Precision Boost Overdrive submenu. Set Precision Boost Overdrive to enabled. Enter the Curve Optimizer submenu. Set Curve Optimizer to per core. Set Core 1 and Core 3 Curve Optimizer sign to positive. Set Core 1 Curve Optimizer magnitude to 5. Set Core 3 Curve Optimizer magnitude to 10. Set Core 6 Curve Optimizer sign to negative. Set Core 6 Curve Optimizer magnitude to 5. Then save and exit the BIOS. We use the Shamino boost curve and SuperPi to check the CPU boost behavior and per core maximum effective clock frequency. By setting the Eclk frequency to 107 MHz, the new maximum boost frequency increased to 5.4 GHz. All CPU cores can achieve an effective clock frequency above 5.3 GHz. 2 cores almost hit 5.4 GHz. We also find that the one-thread boost is now over 5 GHz, and the boost curve has increased by 250 to 350 MHz compared to stock. We reran the benchmarks and checked the performance increase compared to the default operation. As I've demonstrated in plenty of SkatterBencher guides, combining Precision Boost Overdrive with asynchronous Eclk has proven to be the most complex yet most effective OC strategy for Ryzen 7000 CPUs. Generally, we get the most significant performance uplift in single-threaded and all-core workloads. That is exemplified with this 7800 X3D, as we see a plus 7% improvement in single-threaded workloads and a maximum performance improvement of plus 10.71% in Geekbench 6 Multi. When running Prime 95 small FFTs with AVX 512 enabled, the average CPU effective clock is 4593 MHz with 0.932 volts. The average CPU temperature is 71.1 degrees Celsius. The ambient and water temperature is 26.5 and 31.2 degrees Celsius. The average CPU package power is 90.2 watts. When running Prime 95 small FFTs with AVX disabled, the average CPU effective clock is 4855 MHz with 1.001 volts. The average CPU temperature is 86.9 degrees Celsius. The ambient and water temperature is 26.5 and 31.8 degrees Celsius. The average CPU package power is 94.4 watts. In our final overclocking strategy, we will pursue a manual overclock. And that may come as a surprise to some of you because officially, Ryzen 7000 X3D CPUs do not support OC mode. In fact, if you go into the BIOS, you'll see that there's no way to manually set a CPU ratio. However, we can mimic OC mode by disabling the Precision Boost technology so the CPU works at its base frequency of 4.2 GHz. Then we can use asynchronous Eclk to overclock our CPU as if we were in OC mode. Do note though that by disabling Precision Boost, we also lose the benefit of that really high single-threaded boost frequency. So whereas the 7800 X3D can boost to 5050 MHz when Precision Boost is enabled, in our manual overclock, the maximum boost frequency will be our fixed frequency. Now, to understand how we can overclock this 7800 X3D in manual mode, let's have a look at its clocking and voltage topology. The clocking of AMD Raphael is similar to the previous generation of Zen 3 Vermeer desktop CPUs. The standard Raphael platform has a 48 MHz crystal input to the integrated CGPLL clock generator. The CGPLL then generates a 48 MHz clock for the USB PLL and a 100 MHz reference clock for the FCH, which contains the CCLK PLL for the CPU cores and several SoC PLLs. The CCLK PLL 100 MHz reference clock drives the 200 MHz VCO, which is then multiplied by an FID and divided by a DID. As a whole, this provides CPU clock frequency granularity of 25 MHz. As with Vermeer, each CCX has its own PLL, with the cores within that CCX running at the same frequency. In a typical operation, all cores within a CCX will run at the same frequency. The effective clock will differ if the core is in a different P state. The SoC PLLs include a wide range of PLLs on the I/O die. The ones most relevant for overclocking are Fclock, Uclock, Mclock, and GFX clock. The SoC PLLs are not particularly relevant for manual CPU core overclocking. Raphael supports up to 2 external clock modes. They're called Eclk 0 mode and Eclk 1 mode. In Eclk 1 mode, one clock provides the 100 MHz input for the CPU PLL, and another provides the 100 MHz reference clock for the SoC PLLs. From the voltage topology perspective, Zen 4 Raphael is very similar to Zen 3 Vermeer. The processor still relies on a combination of internal and external power supplies to regulate the voltages. There are 4 primary power supplies from the motherboard VRM to the processor. The VDD-CR voltage rail provides the external power for 2 internal voltage regulators, VDD-CR CPU and VDD-CR VDDM. VDD-CR CPU provides the voltage for the CPU cores in the CCX. On CPUs with multiple CCXs, each CCX has its own VDDCR CPU voltage rail, but the voltage will be identical. The voltage rails can work either in regular or bypass mode, but it is always in bypass mode on Raphael. That means the voltage is always equal to the VDDCR external voltage. The VDDCR voltage rail can be directly controlled via the SVI3 interface by CPU configuration. The end user can also directly control the VDDCR voltage rail, as the motherboard BIOS provides the means to program the voltage regulator directly. Choosing the appropriate manual voltage will always be a trade-off between increasing the overclocking headroom, dealing with the thermal issues or thermal challenges related to increasing the voltage, and of course, consideration of the CPU lifespan. It's with that last thought that we kick off our manual tuning process. Ultimately, the thermal solution will be our main limitation, and that's because power scales exponentially with voltage and temperature scales somewhat linearly with power consumption. The limiting factor for our voltage will be our worst case application or worst case stress test scenario. In this case, I pick my worst case scenario to be the same as any of the previous overclocking strategies. Prime 95, small FFTs with AVX512 enabled. The next step is to check the maximum temperature when running our workload and increase the operating voltage if there's thermal headroom. Once we know the maximum voltage, we can tune the Eclk frequency until the applications show instability. In this case, we end up with an Eclk frequency of 114.3 MHz at a voltage of 1.035 volt. That results in a CPU frequency of 4.8 GHz. Upon entering the BIOS, go to the Extreme Tweaker menu. Set AI Overclock Tuner to EXPO 1. Set Eclk mode to asynchronous mode. Set BCLK2 frequency to 114.3. Set memory frequency to DDR5 6200. Set CPU core voltage to manual mode. Set CPU core voltage override to 1.035. Then save and exit the BIOS. We use the Shamino boost curve and SuperPi to check the CPU boost behavior and the CPU per core maximum effective clock frequency. When we perform a manual overclock with a fixed frequency, unsurprisingly, the frequency is fixed across the board and for each core. We rerun the benchmarks and check the performance increase compared to the default operation. As expected, we see a performance deficit against stock performance in single-threaded applications as manual overclocking loses the benefit of the Precision Boost 1T frequency. In multi-threaded applications, however, we see a nice performance uplift of up to plus 8.63% in Geekbench 6 Multi. When running Prime 95 small FFTs with AVX512 enabled, the average CPU effective clock is 4,799 MHz with 1.022 volts. The average CPU temperature is 85.7 degrees Celsius. The ambient and water temperature is 26 and 31.9 degrees Celsius. The average CPU package power is 101.6 watts. When running Prime 95 small FFTs with AVX disabled, the average CPU effective clock is 4,794 MHz with 1.028 volts. The average CPU temperature is 91.8 degrees Celsius. The ambient and water temperature is 26.8 and 30.4 degrees Celsius. The average CPU package power is 91.8 watts. In this overclocking strategy, I've shown you how to think about or how to go about manually overclocking your 7800 X3D. But of course, if you don't care about Prime 95 with AVX512 enabled stability, you can always pick another test as your worst case scenario. For example, in Final Fantasy XV, I could run 5.1 GHz with 1.15 volt and a maximum temperature of 70 degrees Celsius. However, I must emphasize that the Ryzen 7 7800 X3D processor is very sensitive to voltage. Even if you increase the voltage a little bit, you will very quickly run into thermal issues. In my experience, anything over 1.15 volt isn't really usable in a daily situation, as you will very quickly hit the TJ max. The Ryzen 7 7800 X3D may also have sufficient headroom to satisfy the competitive overclockers and benchmarkers. I could push this CPU up to 5.6 GHz with water cooling. Alright, let's wrap this up. At the very beginning of this video, I said it was ironic that the 7800 X3D processor turns out to be the most tunable X3D processor yet. And I stand by that comment, given all of the overclocking strategies we went through in this guide and how locked the 5800 X3D was. So we have to give credit and say thanks to the folks at AMD that decided to give a little bit more performance leeway for the Ryzen 7000 X3D processors. I genuinely enjoyed exploring all the various ways that we could extract more performance out of this CPU. And I really feel that the more you go down the rabbit hole, the more effort you put into fine-tuning, the more extra frequency and performance you can find. But I must again raise your awareness or point your attention to the fact that voltage is the real main danger for the 7800 X3D. Realistically, I don't think any voltage above 1.15 volt is going to be good for your CPU. Good in a sense that it will not cause you to hit TJ max. Anything above 1.15 volt with any kind of a medium to high workload really pushes your CPU to the maximum temperature. If you go beyond 1.15 volt, then thermal choking might genuinely damage your CPU. So be very careful if you want to go over 1.15 volt. Anyway, that's it for me today. I thank you for watching and I thank the patrons for their support. As per usual, I will put up a written version of this video up on my blog if you want to go through the BIOS settings or check the performance results. If you have any questions, drop them in the comment section below and see you next time.